Hey guys, welcome back to the YouTube channel. Today we're going to be talking about redox reactions. We're going to talk about two things relating to them, what they are and how to balance them. Now, what are redox reactions? Redox reactions are any kind of chemical reaction that involves the transfer of electrons from one thing to the other. What ends up happening is that one thing is losing it and one thing is gaining the electrons. And so we have this two words to describe these two things, which are oxidation and reduction. This little acronym here, OLRIC, helps to memorize which is which. It stands for oxidation is losing electrons and reduction is gaining. That's the sort of acronym you want to know. So this is the chemical reaction. We're going to balance it, and these are the steps we're going to follow. First off, we're going to look at oxidation states. Oxidation states are the hypothetical number of electrons associated with each atom. And we look at oxidation states so that we can track where is it going. So if it goes from here to there to here, so we can know what is being oxidized and what's being reduced. That's the goal of step number one. One thing to note though is that for a molecule like this, where like CO2 doesn't set, so this number at the top, this 3 plus indicates the overall charge of this sort of thing right here, right? So in this case, this is CR, the overall charge is 3 plus. CO2 doesn't have anything right there, which means that its overall charge is 0, it's neutral. If there was something such as H2, and this is just hypothetical, and there's nothing there, it would be neutral because there's just nothing there. Whereas for these things, since they say 2 minus 2, this means that its overall charge, its net charge is -2, and this also says -2, so its net charge is 2. So whatever the oxidation states of the individual atoms in this molecule are, they have to all add up to equal -2. And for this, they have to all add up to equal 0 because it's neutral. So what we're going to do is we're going to assign the oxidation states to each one of these so that we can track where the electrons is going, so that we can determine what's being oxidized, what's being reduced, so that we can write the half reactions next. So first, in order to know what the oxidation states are for each of these, you have to figure out what you do know, what you don't know. What you do know is that the oxidation states for everything typically is going to follow this pattern here. If it follows under this column, for example, it's going to be +1. If it falls under this column, it's going to be +2, and so on and so forth. And so not everything, as you see, all of this is blank, so you don't know what that is. But if you look over here, so what is this? CrO. So we have oxygen and then this. But since Cr is nowhere on here, but oxygen is, we take what we do know, which is the charge of oxygen, and we use math to figure out what this is. So for this, we know that the overall net charge is going to be -2. We know that based off of this, oxygen is going to be -2 for each oxygen. So what that means is that since there's 7 oxygens, that means that 7 times 2 is equal to -14. And it's going to have to equal 2. So whatever this is, it's going to be positive in order to counter this to make it less negative. But whatever this is, it has to add up with -14 to equal -2. Now, mathematically, what would that be? That would be plus 12. And so then we can go over here. So what is this? This is oxygen. Oxygen, again, is going to be -2. There's 4 of them, so it's going to be -8. And since the overall charge is -2, this is going to have to be +6 overall and +3 for each individual one because there's 2 of them. So +3, so this is each carbon atom is going to have the oxidation state of 3, and since there's 2 of them, that's going to make 6. And the 6 with the -8 of the oxygen is going to make -2. So you look over here, this one's a little more simpler. It kind of just tells you it's 3 plus, so this is going to be +3. And then CO2 is going to be, in order for it to have a net neutral charge of 0, the oxygen is going to be -4, because again, each oxygen is -2, and there's 2 of them, so there's -4, and this is going to be +4 in order to counterbalance the 4, the negative. So now we've got the oxidation states written out. We are going to try to write out half reactions. What are half reactions? Half reactions is basically this whole chemical equation divided into 2, in terms of one is the oxidation and one's the reduction. Now, before we do that, we got to figure out which one is which. So again, oxidation is losing electrons, which means it's going up in charge. So if we look over here, let's look at this. Cr is +12 here, and then on the product side, it is +3, which means its charge went down, which means it is being reduced because it's gaining electrons in order for its charge to go down. So we can write the half reaction for that, which is Cr O7, -2, which is what this was, becomes Cr3+. And again, reduction is gaining electrons. So as you can see, the oxidation state in this is going from +12 to +3. In order to do that, it's becoming more negative, and to become more negative to gain electrons. So this is the reduction half reaction right here. And then obviously, if this is the reduction, that just by default means that this has to be the oxidation. So we're going to write it out. C2O4 2 minus becomes CO2. Now again, this right here, you're losing the electrons, so it becomes more positive, the oxidation state, and this is reduction, which means it's gaining electrons, so it's becoming more negative. So that's the first two steps. We wrote out the half reactions. Now we have to balance the mass using, so first we have to balance the mass of everything but oxygen and hydrogen, and then we'll balance oxygen and hydrogen. So let's do this one first. So over here, you see on the reactant side, there's 2 carbon atoms, and on the right side, there's only 1. So we're going to put a 2, so there's 2 carbons on each side. And as you can see, now there's a 2 here, the 2 times the 2 here, the oxygen means there's 4 oxygen atoms total, and there's 4 oxygen atoms total here. So that means everything's balanced out here mass-wise. If you look over here, there is 1 of each of the CR. However, there's 7 oxygens over here, and there's no oxygens over here. And so since it says right here, balance mass using H2O, we're going to use H2O to balance out the O's because there's an O in H2O. So we're going to write 7H2O. So that now there's 7 oxygens on each side. However, the problem now becomes that there are 14 hydrogens here and then none here. So we're going to have to write 14H plus, because again, for the hydrogens, we're going to balance it by adding H plus. So now there's an equal amount of hydrogens on each side. There's an equal amount of Cr and of O. The next step is to balance the charge using electrons. So in order to balance the charge using electrons, you're going to have to know what the charge is on each side total-wise. So if you look here, 7H2O. H2O, there's no number right here, which means it's neutral, so that's 0. It doesn't contribute anything. Here over here, the Cr3+, the 3+ indicates that there is a charge of 3+. So this product side is going to be +3. You look over here, there's 14H+. It's kind of hard to see. And there's -2 here. So when you put those two together, you get 12+. And so since there's a difference between here, they're not equal, we have to balance using electrons. And so the way we do that is we are going to add electrons to the left side so that it comes down to be equal to the right side. And so I'm going to write it real quick. 14H plus CrO7 minus 2. And again, I'm just rewriting this. And so since there's 12, the net charge over here is 12 and there's 3, we're going to be adding 9 electrons so that they equal each other. Yields Cr3 plus 7H2O. And again, I add the electrons on the left side rather than the right because the left side is more positive, as you can see with the 12 compared to the 3. And we want them to equal each other. So by adding 9 electrons, it goes down to 3, so they're equal. So again, this is the reduction. All I did is I rewrote this. I rewrote this one, this equation right here, and I put it down here, adding the electrons. So let's do exactly what we just did for the oxidation. So for the oxidation, we're actually going to add electrons on the right side because as you can see for this, it reads C2O4 with a -2 charge yields 2 CO2. Again, there's nothing here on the CO2 that indicates that it has any kind of net charge. So its net charge is neutral, so it's 0. So you have 0 over here, and then over here you have a -2 charge, which is, they're not equal to each other, but we want them to be equal to each other. So what we're going to do is we're going to add electrons, and we're going to add electrons to the right side so that they're both -2. So we're going to rewrite it. C2O4 2 minus yields 2 CO2 plus 2 electrons. So now that we did that, the net charge on each side is equal to each other. In this case, it's -2. So if you look back at the steps here, we've done anything. We've assigned oxidation states like this. We've wrote out the half reactions of the oxidation and the reduction based off of which one's being oxidized, which one is reduced, which is based off of the flow of electrons. We've balanced the mass using H2O and H+. We've balanced the charge using electrons. And then for the final step, we're going to add the half reactions. In other words, we're going to add these two half reactions together to get the overall reaction. But before we can do that, one of the things we have to do in order to add these two together, where the reactants go through reactants, products go through products, is that we have to actually multiply them by a coefficient, so that we have to multiply everything like on here and here and everything right here and here by a coefficient for each one, so that the number of electrons equal each other. So let's do that. We're going to put it in parentheses so that you can kind of see what this is happening mathematically. We have to do the lowest coefficient that it can equal each other. In this case, it's going to be, I'm going to multiply this one by 9 and this one by 2, because if you look here, there's 9 electrons here and there's 2 here. And we want them to be the same number so that they equal each other, so they cancel out. And so the lowest common denominator number that they equal each other is 18. So we're going to multiply this by 9 times 2 equals 18, and this times 9. 2 times 9 is 18. So then we got to rewrite everything and multiply it by that same coefficient for each. So what's going to end up happening is you have 2 times 14, so that's 28H plus 2Cr7, 2 minus plus 18 electrons yields 2Cr3 plus 14H2O. And then for this, we're going to multiply 9 by all of that. So it'll be 9C2O4, 2 minus yields 18CO2 plus 18 electrons. And see, so by doing that, what we ended up doing is that there's electrons in this first equation, there's electrons on the left side, and on this second equation, electrons on the right side. And since they equal each other and they're on the left, one's on the left, one's on the right, that means they cancel each other out, which means we can erase this. And then now we can actually add the half reactions with the charge being balanced. So we're just going to do that. We're going to add these to be added together because they're both reactants, and then these are both products. So we're going to add them together. So plus 2Cr7 to negative plus 9C2O4 to negative. And then I ran out of room, so I'm just going to write this. This would all be right here. 2Cr3 plus 14H2O plus 18CO2. And that's it. That's the balanced equation. The idea is that we wanted all of the electrons to be balanced and the mass to be balanced. And that is it. The number of electrons lost in the oxidation half reaction now equals the number of electrons gained in the reduction half reaction.